Okay, so welcome everybody and to our PCB and KiCad training, the last part, or let's say the nearly the last part, the review of the submissions. The last part, of course, is going to be the submission of your production data in order we can produce your PCBs. I'm quite happy that after April, we had a very good response. In total, I think I received 23 or 24 PCBs from your side. And it was a very overwhelming reaction or overwhelming part, because I didn't expect so much PCBs feedback. So thank you very much. And I went through all PCBs designs, and in these slides I put together the, let's say, common findings or common issues I found in the schematics or in the PCB. So what I will do today with you, I want to make a schematic review. So I will talk about a little bit about some findings or some best practice you should maybe change for your next design. I will talk about layouts, maybe some good stuff and some maybe not so good stuff I have seen in your layouts. And at the end, I want to also speak about mechanical aspects which should be taken into account in your designs. And last but not least, I will talk about the Gerber submission. So when you, after this review, adapted maybe last time your PCBs, you can send me your Gerber files, and I'm going to produce these Gerber files, or our partner, LA Conta in Stuttgart, is going to produce these PCBs for you, and I will ship them to Valencia in starting of June. Good, so this is our topics for today. Do you have any questions beforehand from your side? If not, I would continue. And if you have any question, just raise your hand or write a comment in the chat or open up your mic and say, 1 second, I have questions about this, I have questions about that, and we directly discuss your questions. At the end, after the slides, if you like to present maybe your schematic or your layout, or you find something we haven't discussed in your design, you're open or free, if you like, to share your design and discuss your questions on your schematic or layout as you like. So we are open at this point. Good, let's start with the schematic review. First, I found some schematic information. This is the first slide. Here we see that in your schematic, you have the schematic window and the schematic title. And here in this title page, you should put a little bit more information. So at least the project name, we have this project name, any 555 timer, pinging LED, that's fine so far. But additionally, you should put the date when you worked on it the last time, the revision, so what version does it have. For example, when you start a project, you can start with 0.0 or 0.1. You put the name of the designer, because later on, let's talk about or think about your working in a bigger company. So maybe you input the schematic and somebody else is doing the layout. And then it's very handy that the guy who's doing the layout can contact the designer of the schematic if he has any questions regarding the schematic and the intention of the designer, why he designs this in this way or that way. So that's maybe you should always fill out this project designation sheet, or this title page or title area of your schematic. What I found quite often was some notes for layouting. For example, mechanical information, board dimensions, mounting holes, and how many layers should be used. This is quite what you need to add. Also, for example, information about the layout on its own. Connection between two signals should be as short as possible. So this kind of layout information, let it be here the mechanical information or some information about how you should trace your tracks, or how you should route your tracks. Maybe also there should be some impedance match tracks, or there should be some tracks which should be shielded somehow from the other tracks. Or if you have some sensitive sensor signals, they should be put away for switching devices like switching regulators or clocks. So all this information, which you know as a designer who designed the schematic, should be put on the schematic on this nickel line in order the layouter knows how to treat this special net or this special trace. Keep in mind that the schematic is maybe the major communication or information you exchange between you and the layouter, or it should be exchanged between you and the layouter. Good. Then one thing which I think I haven't seen at one schematic. Everybody puts this connector, that's fine, but nobody talks about what's finally the supply voltage. I mean, I think I said it should be 9 volts or 5 volts in the exercise, but put it also on the schematic somewhere, just close to the VDC and ground connector. You can write here VDC is 5 volts or 9 volts. So this is clear. This I missed a little bit. Good. Schematic design annotations. I found a lot of the power indicating LED between VDC and ground, the resistor R1, the LED, but only a few from you decided or designed it. It's I have seen a lot of submissions where you put R1, but you didn't fill out the value of R1. So some of you put 360 ohms, some of you put 50K or 50 kilo ohms for the current limiting resistor in front of the LED. So my question to you, I don't know if somebody is here who submitted the 360 ohms resistor. How did you calculate this value? Or how do you derive this value for the power indicating LED between the supply voltage and the ground? Can somebody tell me, or? Somebody here who designed this circuit? Yeah. Okay, so one puts 330, okay, and why? Can you explain or justify or let's say comment on a design decision? Okay, K-rate was 350, so you took the next value available in the norm series, fine. So your colleague just wrote me a message that he says I put 330 because I calculated 350. And how did you calculate this 350? No? So what I prepared is because I haven't seen this, I didn't saw a lot of annotations on this, so I just want to do this together with you now, how to calculate these values of the current limiting resistor, because I have seen this only a few times. The value, the most of the time I have seen only R1, and the resistor values or the resistance values has been left opened. So if we want to calculate the resistance value of an LED, the first thing you should do is you go to the data sheet. So I put here, or you see here, the data sheet of an LED, and you see the features, low power consumption, general purpose leads, and so on. You see as a emitting color deep red and lens color diffuse red. You see the packaging information and the symbol, polarity, everything we need for the mechanical stuff. And now we come to the absolute maximum ratings. So these are the ratings you should not, you shouldn't leave, or you should keep at the end. And what's interesting for us is, of course, here the peak forward current, so the maximum current, which can be withdrawn from the diode, then you see peak forward current. Peak forward current means this is only a current which is only in a very short of time put on the LED. And what's mainly interesting for us here is this DC forward current. Oh, sorry. Let's do it like this. Peak forward current, this is this one, but what's interesting for us in our case, doesn't work. I'm sorry. Is it working? Okay. Doesn't like I use my pen. So what's interesting for us, of course, is the DC forward current. So this means a continuous current the diode is going to digest, if you want to say, and this is going to be 25 milliamps. So we take in mind maximum current we should subject to the diode is 25 milliamps. Okay, if we look at the forward voltage, so if we have it now our diode, our LED, right? And now we know that the current flowing here is 25 milliamps max. Can somebody tell me what we should assume here for the forward voltage? So what's the voltage drop typically at an LED? I don't know if we have talked about this when I have been in Valencia at your place. So what's a typical value we assume for the forward voltage across a diode, the light emitting diode? Any idea? Just tell me it's 1 volt, 2 volts, 5 volts.
1.5.
Yeah, 1.5. Yeah, it's very important. It's going to be something between 1.5 and 1.8 volts. So if you take 1.5 as a rule of thumb for the beginning, it's perfect, 1.5. Right, so in general, we can assume the 1.5. If you want to do it a little bit more accurate, you can go to the data sheet. And if you scroll down, you found here a graphic forward current and forward voltages. And here you can pick out a working point which you like to use in your design. And in our case, which is quite interesting or very easy to use, is here the 20 milliamps forward current, and then we have a forward voltage of 1.8 volts. So this is what we assume in our design. Good. For this, I copied out this graph here. So we say in our case, we take as a working point the 1.8 volts at 20 milliamps. So we take out of the data sheet IF is going to be 20 milliamps, and we keep in mind that 25 milliamps was the maximum we should apply to the diode. So this is smaller than the Imax, which is going to be 25 milliamps. And we take the forward voltage VF is going to be 1.8 volts. So when we have all this information, then we can calculate our resistance, current limiting resistor. And for this, we just have to look up again. Yes, just again the supply voltage we have assumed, yeah, so we assumed the 9 volts. So if we want to continue now, we say we have our 9-volt supply. And let's take here our current living room resistor R1, which we have to calculate. And then we have here our diode, light emitting diode. And we say now, here we take the 20 milliamps as a current through the diode. And we take the 1.8 volt for the forward current. So how do we calculate now R1? If we have here a voltage drop of 1.8 volt, the rest of the 9 volts is going to be dropped at the R1 at the current living room resistor. So this is going to be 7.2 volts. Okay, so now we know this is going to be 9 volts minus V forward divided by I forward. And this is 9 volts minus 1.8 volt divided by our 2 milliamps. And this is 7.2 volts divided by 20 milliamps. And finally, I haven't calculated yet. I have to calculate on my own now. 7.2 divided by 20 milliamps gives us 360 ohms. So we are quite close to what your colleague just sent it to me. The 350, he calculated 350. So maybe he has assumed here not 1.8 volt, but 1.7 volt or something like this. So you see, this is 360 is quite reasonable in our case. If, for example, what's going to be likely, what's likely is going to be happening is you go to a lab and you take one diode out of your box, but you don't have any data sheet and you don't know what's the forward voltage or the current. So as a rule of thumb, you can assume for your forward voltage, we forward approximately what your colleague says, 1.5 to 1.7 volt. And if you take as a forward current something between 10 milliamps to 15 milliamps, as a rule of thumb, if you don't have a data sheet at the hand, you can take these values in order to calculate the current limiting resistor if you don't have a data sheet. And if you stay in this range, it's mostly, it's likely you don't destroy the diode at the end. Okay, questions so far to this part, how to calculate this current limiting resistor in front of the LED? Okay, no question. I think it was straightforward. I just wanted to review it. Maybe you haven't been so familiar with it. I don't know. That's why I just say it's a quick talk. And yeah. Okay, very good. Then let's go to our review, our slides. So we talked about the current limiting resistor, and we talked about the 360 ohm. Somebody took 15K, also 15 kilo ohms. That's also possible. And I was wondering if it's still working. And last year in the lab at our university, some students also pick a very high current limiting resistor, also in the order of tens of kilo ohms. And I was wondering if it's still working. And then we go to the lab and we applied this high resistance values to the LED, and indeed it was still working, and it still was lightening, and you could still see the LED working. Of course, it's not so bright anymore, but it's totally fine if you also take higher resistance values. So that's fine. Good. Then let's go to the schematic design annotations further. Minor parts. I mean, this, of course, if you put your traces or your lines, your connections like this, your wires, that's fine. Yeah, with the spans or with 2 bands like this, is electrically it's working, but it's not a really clean design. And it's something how shows a little bit how tight you work. And if you go to somebody else who should read the circuit, I think you want to make a good expression to him, so try just to tidy up a little bit that you don't have such turns and bends which you actually don't need, and gives you maybe odd picture of your schematic. Yeah, the same here again, not tidy. Also look that if you have text and annotations, that this text and annotations doesn't override the values of the pictures or diagrams, symbols of other components, or if the texts are overlapping, that's not really nice because you cannot really read it. Here we see one example of a design which was quite good. Personally, I wouldn't have put this so dense together. I would have scratched it a bit out, but this design was actually not the design I explained you in the YouTube videos. So here the students checked out what else or what different possibilities he has, or looked for another circuit with the any 555 timer LEDs. And in the circuit we designed in our course or in my YouTube videos, it was one blinking LED. So we had a blinking LED, one was blinking, and in this circuit, has somebody an idea what's the difference, what's happening here? You have a red LED and a green LED, and it's also connected to the output Q of our latch or flip-flop. So how is this circuit working, and what do you observe if you power up the circuit? Has somebody an idea? I don't know if I think yes, I think the student who designed it is also attending the class, right? If I'm right. So the student who sent me this circuit diagram, can you explain it? What's happening with these two lights? Yeah, I know. Yeah, perfect. Can you explain what's happening with these two lights if you power up? Okay, so he's here, but the microphone is not working. Okay, so I'll take over his part and explain it. If you power up, of course, this Q, the pin number 3 Q, at half cycle, it's going to be at a positive supply voltage, and on the other half cycle, it's going to be on the negative supply voltage. Okay, so you have the square wave at the output, and if you put now this square wave to this combination in the middle here, and then you have here a red diode or a red LED, and here a green LED. So what's happening with these LEDs if at the output changes between 9 volt and 0 volts when it's toggling? What's happening with these LEDs? Can somebody tell me what's happening with these LEDs? Yeah, exactly. I got the answer in the chat. This is correct. Somebody else has an idea before I tell you? Imagine, just imagine you put at this node one time a negative supply, or let's say you put one time you put it to ground, and one time you put it to 9 volt. What's happening with the red and the green? Okay, two answers, and both are right, so we'll explain everybody. this LEDs are going to blink alternatively. Yeah, so either it's the red is powered up or the green is powered up. So it changes red, green, green. And this is because if you check, if you have here now ground or 0 volts, then the potential of Q is on this ground. So the green LED is off and the current can flow from the positive supply through the red LED through R3 into our device towards ground. And the next half cycle, Q is going up to 9 volts. Then the voltage across the red LED is going to be 0 volts because we have here 9 volts, we have here 9 volts. So the difference here about this branch is 0 volts, so no current is flowing. But here we have 9 volts regarding ground, so current is positively flowing in this direction. So then the green LED is going on. And so it's alternatively blinking the red and the green and the red and the green zone. So thank you very much for the submission. I like this alternatively design here. And what I also liked at this design was that he put 2 test points for ground. Why? Imagine you get back your PCB later on, and then you want, for example, test your device. And we put here some test points at TR for the charging and discharging, or for the output. And for the output, and one for the charging and discharging. This is for the charging and discharging, and normally you should also put one for the output. Let's say you want to test here and to see how the capacitor is charging and discharge and charge and discharge. Then you need a connection between ground for your oscilloscope probe and this test point. So you need, let's say, 1 ground and 1 test point here. Then you want to see the output voltage at Q. So you need a second channel of your oscilloscope, and you connect the ground connection and Q. And like this, you have you can check these 2 voltages, but you see, if you want to use different measurement equipment, you also need, or mostly need, a ground connection. And that's why it's a good idea to put at least 2 or 3 ground pins on your PCB, also not on one side of your PCB, but scattered around across your PCB. Like this, you can access ground and test a signal regarding to ground. So in my designs, I put normally at least 3 ground pins, because if you have an amplifier, for instance, you want to test see the input signal and you want to see the output signal. And then you need at least 2 test points. And maybe with a multimeter at some stage, so you also want to test the supply voltage or a DC voltage somewhere, and then you need a third test point. So put some test ground points on your schematic and on your layout on the PCB. It's quite good idea. Well, okay, schematic. Then schematic export. Here, it should be ERC free. I found some submissions. I did an ERC check for all designs. So if you have here an ERC error, then when you go to the layout editor, and you have already the input an error. Of course, you can say maybe this error is not causing any problems in the layout, but it's unsure, right? So make sure before you start the layout that you have an ERC-free schematic. Okay, so this is quite important. Please take care that it's ERC-free. In this case, I found here a label, and it was put into nowhere. The rest of the schematic was somewhere on the left. And when I put the ERC, it came up here with this error output label, but it's not connected to anything. Interestingly, I found this error several times, and the circuits also look quite similar. So I don't know if you shared information to each other, that's fine, but make sure when you submit that you at least resolve all errors or problems found. Good. Next thing is here. The problem here was that passive line pin not connected. This is something maybe I haven't talked about it in the class or in the videos, but here, for example, the test point is connected. You see it by this green circle. And this test point is not connected because he has no green circle. And it's put on, let's say, the connection wires of this capacitor. So you have no connection to the signal is just placed at the point where it's you can place it, but you make no connection to any signal. This is also something what to look for or to avoid. Personally, what I do is I try not to cross the connections of two components at one point. I also always put a little bit wire or tracks between. Like this, you get always one of these dots or the green circles for each connection. Right? So if you, for instance, move this capacitor a little bit to the left, you get here also this green connection trace or this green signal line, and then you get also a green point for this test point, and then everything is clear. So just what maybe I haven't explained it quite well, but in order to avoid these errors, don't put the connectors of different components together on one point. Keep a little bit distance and wire them. And if you have really a connection and a crossing, then you automatically get this green dots. That's the same problem here, for example. Indeed, it's connected because you don't have a crossing. You have here one wire, and it's connected to this test point here, but the test point is turned by 180 degrees. Normally, the circle should be down here, and then you have the circle, the brown connector of this test point, and then going into the green wire for the wiring. But here it's turned, so it's connected, but it looks somehow strange. And first I thought it was not connected, but indeed was connected. So in your schematic, check that this is straightforward and is not misunderstandable. And here we go back to the ERC errors. For this, for example, it's ERC free, but I was wondering if it's connected or not. So this is maybe the two things you should pay attention at. Make ERC free before you go to the next step, layouting, and check that you have drawn readable and understandable schematics where no questions are arising if you look at them. And as I said here, is a question. My question was, a question arises to me: is it connected or not at the end? Good. Then, any questions about schematic annotations and schematic review part from your side?
I have a question regarding one resistance.
One resistance, yeah?
The other LED had a resistance defined of 330. Should that be changed to 360, or is it okay that?
No, you can stick to 330. I mean, I calculate now 360. If what you can do is, if you like to, you can wait. Okay, just go back to my calculations. What you can do, for instance, is you can take. No, I have to. I need a pen. 1 second. So, what you can do is you use now. You take this equation, okay, and you resolve it for IF, for example, and say, okay, I stick to 1.8 volts. And you resolve the equation for IF, and you put for R1, you are 330. And you can see if the resulting current is above the 20 milliamps or not. Then right. you can cross-check if 330 is still fine, but my feeling says yes. If you check, and on the other side, if you check here on our forward current versus forward voltage graph, if we check the 25 milliamps, it's going to be here. Yeah, so you have plenty of design space, nearly 0.2 volts Yeah. So my stomach feeling says it's no problem with 330. But if you want to cross check it, you can do it in this way.
Okay.
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 Fine. Good. More questions from your side? Fine. If you have no questions, we continue with the next slides. We come now to the section layout review. Layout routing, exactly. Here we on the top, let's say here it's avoid unnecessary bends and turns. So if you see here, I think it was a resistor and a diode in parallel. What you see is this through hole and plated circles for the soldering. And what you can see is here, the centers are not aligned of these two circles. They have the same diameters, but they are not aligned. So by layouting or by routing, you make here this extra band. So that's not really nice and handy. I would avoid this by moving this a little bit down, for example, and to get this unnecessary bands out of your designs. Of course, if these two components have, and on the other side, if they are really in parallel and the package has a different size, maybe the holes have different distances, then you have to bend somehow. But I would avoid this and keep them together on the same level, that the center is on the same level, and then you don't have this extra bends. I found test points like this, two test points, ground and VDD next to each other. The idea is not bad, but the problem is they're connected to nothing. I don't know, you cannot read anymore. I think here it's not connected. So yeah, you put a test point on the board, but you didn't connect it to any signal or ground. So it's just a mechanical point of view. So this was something finding where I say, okay, this also gives you errors when you make the design rule check. So this could be avoided. And then I have this, it's a classical topic. I have in all classes, students try to use the auto route function. I mean, it looks quite handy, right? You make the schematic, then you go to the layouting, you say, okay, this is my rectangular PCB. You move all the components within the PCB, and then you mark it and you say make auto routing. And of course, the computer is intelligent enough that at the end, all components or all signals are connected to each other. But maybe the way how to connect them is not the most efficient or the most cleanest way. To see this, we can follow, for example, here this red line, or let's say from two, let's say the red line. So it goes here up between these two pads, around this capacitor, around this test point to this ground pin. Okay, and if you see how it's routed, it turns out exactly at the position where it's allowed to do. So there's no, let's say, security margin or let's say some design margin left. It's just cutting the edge. And if I see this, I know that auto routing was used. So of course, electrically it's connected, but it's the way to route it quite a long way and around, let's say, to make a 360 degrees turn. So that's a pretty clever design or clever routing. So keep this in mind. The auto router can be used, for example, if you have a parallel interconnection between two devices, digital interconnection with, let's say, 18 bits or 16 bits in parallel. And then on your board, you must make 1, 2, 3, and so on, all by hand, and maybe also a little bit going up and going down or making a curve. Then it's, let's say, annoying to draw all the different signals by hand from bit 1 to from bit 0 to bit 15 to route all 16 bits. And in this case, you finish your complete layout and you leave open the digital interface and says, okay, for this 16 signals, I use the auto router and this should be looking fine. So for this case, auto routing is good. But let's say to put all the components in place and then mark it and say, okay, make the routing somehow you like to, it's not really resulting in good layouts and good designs. Good, we come back to this example because it's a quite good example also for other stuff. Another thing which is not so good here is that if you look, you have here the component, of course, the copper is stopping here at the filled section, and here in the crossed out section, this is the part where you don't have copper. And here, this is at the H cut, so here you cut the PCB. And of course, the copper here shouldn't go until the H, or normally doesn't go until the H of your copper. And your device is placed just at the edge of your H-cut layer. And since it's not really stable, since this PCB is cutted with a saw, the component might here be standing out of your PCB. I would place all components that they're always inside the complete copper planes. But just move the C2 a little bit down, that the upper point is also inside the copper, because here in the crossed out area, it's not clear if this area is 1 millimeter wide or 0.5 millimeter wide or even 2, because here you perform the cutting out of the PCBs from this big panel. I mean, the production, I don't know if you're familiar with the production of the PCBs, you are not going to process your 15 centimeter by 5 centimeter PCB. You have a big panel, let's say like an A0 sheet. And on this big panel, there are the different PCBs manufactured, processed. And when you are finished, you cut them out and you get the little PCBs from your design at 5 centimeters by 15 centimeters or 2.5 by 5 centimeters, whatever. And this is why you have this cutting edge here, H-cut, because you have to cut out from this big panels where are a lot of PCB on it. You have to cut out your design. Yeah. Good layout, silk screen. Yeah. Here I found first of all, perfect. You put the test points to test the signal. That's fine. But I would change these test points to meaningful names. For example, here you see at the 1, you see this is the output which you are monitoring. So from our circuit, the pin Q3 or pin number 3, Q or pin 3 from your NE555 timer. But later on, this output here is only for you to see it in the layout program. Later on, you will only see when the PCB is manufactured TP1. So now in our designs, we have only 2 test points normally, the charging, discharging of the capacitor and maybe the output of your NE555 timer. So you can go on with TP1 and TP2, but if you have maybe design with 5 or 6 test points, it's definitely better if you put meaningful names for those test points. So here I would put on the silk screen out, then it's written here out, and when you later go to the lab, you see, oh, I want to monitor out, you look on the PCB, it's out. If you read TP1, TP2, you have to go back to your schematic and to check to what signal TP1 is at the end connected to. I found 1 or 2 who put the QR code or your logo, the picture of your university. That's a nice gimmick. You can do this, of course, because it doesn't change the cost of your PCB if you put this on your PCB. Go for it. It's a nice gimmick. It's a good, yeah, if have fun and if you want to show it somewhere to colleagues, it's also nice to see what you can do all on the surface of the PCBs. Here, what I found here, this is the silk screen printing is very close to the H-cut or to the cover. I will put here just a little bit more distance in order not to have any problems, because if you look on the stacking, you have your PCB material, yeah? Then you have the copper, and on top you have the silkscreen. So if you right now are one directed to the edge, this means that you have here an edge between the copper, and then you go step down to the PCB material, to the fiber and through the glass. So, and if it's too close to this, maybe it gets distorted or corrupted by the step because of the change of material. Here you have copper, and here you have no copper. Silkscreen over the edge or overlap, of course, this is not working at all, since here the silkscreen printing, so the annotations on your PCB is outside of the PCB. This cannot be on the PCB anymore. The same here. This is what I just said, that you have a step from the copper side to no copper, you go down, and across this step you try to print D1, or the part of the D is on the copper and the part is not on the copper, so you have a difference in size. So this might also give you problems with the processing. Yeah, and here you have this ref star for the mounting holes. Also, this is maybe information you don't need, so you just delete it out of your design. Yes, layout, ground filling. This is something which I also seen sometimes, but this is maybe a typical stuff which you do at the first PCB. Try if you pour the copper plate on the top and then the bottom with the ground, try that at the edge of your rectangular PCB, you have let's say like copper frame for all the components in your ground plane. So this means just move this a little bit inwards, move this also a little bit inwards, and move this tracks also a little bit inwards, that the last line here is all the ground copper, which is like a frame around your complete PCB. So, and here what you see is here you have the ground copper, then you have a trace, and then you have nothing anymore, and then your PCB is finished. And by moving this jumper or this connector a little bit inwards, then this ground is like flowing or integrating this connector, and you have also ground here and ground here, and then you have at the edge of your PCB like a ground frame, which is good for EMC issues and gives you good ground potential on the complete PCB. Yeah, then we come back to this auto routing part. You see that here was auto routing was used, and what auto routing was doing is he connected this ground by this line with the ground of your IC, which is electrical logical correct. But after this auto routing, the students makes also the pouring of the ground. And then the funny thing is happening that you have on the one side a trace for ground, and on the other side you connect this plated through hole directly to the ground plane with this connectors. And the same here, you have now the ground connected to your ground plane by this three passes on the left, top, and on the right, and also by a trace which is routed from here across the complete PCB. So this makes, as you see, this makes no really sense. It doesn't make really sense to have this ground connection. Yeah. Exactly. For Gerber generation, I don't know. I think we said that we don't use the SMD components. You can use SMD components if you like to, but it's if you do the first time your PCB, I think avoid SMD because it's surface mounted devices, because it's not very easy to solder by hand. That's the one thing, and the other thing is that here you use, I don't know if it's a plated through hole, I hope so. In your design, you should use only through holes. So it means if you have, you should not use wires or buried wires. Where's the difference? If you have a buried wire, you connect layer 1 and 2, but you don't go through the complete PCB. But remember, we have a 2-layer PCB, so that's fine, because in the 2-layer PCB, of course, it starts on the top layer and goes to the bottom layer. So this is that's fine for our design. I don't know who submitted this. He has to think about, you really want to continue with the SMT part? If yes, just hand it in like this. That's fine for me. But be aware that it's more complicated to solder the SMT part. Fine. Going here back, yes, this is another part, error founded here, error missing connection between items. If you see here, you have here the trace, and here maybe very slightly, I don't know if you can see, it's the fly line. So normally this point should be connected to this pad. It's not connected, it's why this error is thrown. Here holds the same, like I said, from the step schematic to layout. Now we go from layout to the Gerber files for the production data, which is the production data of our PCB. The layout should be error-free, DRC error-free, before you do the next step, exporting for the Gerber files. So in this case, please correct this. And it's clear, I'm aware of that if you cannot do this connection on this layer, because you cannot cross, right? You have here already the VTC connection, and now you want to go with this trace over this connection. But if I think now more clearer, I don't know why you need this connection, because this is D2. I assume this is the power indicating LED, right? So you connect the anode to VDC and the cathode to ground. So if this is the port copper is going to be ground, you don't need this trace. You just connect this pad to the copper here. Yeah, I just observed this. This idea comes just up to my mind. So I'm really wondering which signal is on this trace. Hopefully not ground, because for ground you should be just connect to the copper plane for the filling. Yeah. Good. Fine. Now let's talk a little bit about mechanical aspects. One important thing is accessibility. If you assume you have here a ground pin or even a signal pin, now first assume a ground pin. So if you think about the oscilloscopes, they have your test head where you can probe your signal or the connection you want to probe. And then they have these crocodile clamps. So this clamps like this. So, and this should be connected to ground with clamps. So imagine this is the ground pin. You have to connect this here. So you can come from this direction to connect, but in some cases, this needle or this test point was between high components. So it's difficult to connect these components. So from a mechanical aspect, a few point, check that your test points are can be easily accessed with your test equipment. This means for the ground pins, this is most likely to be such a clamp. Look that the test pins are scattered around your board, maybe at the edge, the ground pins of your PCB at the edge, near the edge cut. So you can easily access them, and then you can access with this clamps this ground point. Here we have a very dense design. Of course, that's possible. The components are quite close to each other. But remember, you want to solder them by hand, and you want to place the components. And if they are so close to each other, it's on the other side hard to solder, let's say, this guy without having any influence on that guy. That's why just to keep them a little bit away. Yeah, so you don't have to make it as dense that these courtyards nearly touch each other or even overlap. Overlap might be bad, because then maybe you couldn't place the component anymore. But also keep here some distance, right? That it's not so tight, your design. It's not so dense. Yeah, here is another example of component over the board edge. if you are aware, you can do this, but mainly this PCB is somehow in a case or in a casing, and then it's not good if some components are outstanding your board edges. Also for stability, it's an issue. I mean, for an LED, it's not that big issue, but in general, check that your components doesn't outstand your PCBs. Any questions to the mechanical aspect? Oh, sorry. Of course, we go back. No, we start here. Any questions to mechanical aspects from your side? Okay. And any questions regarding your layout, or somebody has questions about the layout? Okay, if it's not the case, we continue. So now we are finished. I give you some feedback on your schematics and layout. You can now change your layout regarding the stuff we discussed. Oh, one question comes up. Was there any problem with the connections between layers or only the SMT components? No, there was no. If you go back, this was only that SMTs maybe, if you solder the first time, maybe a little bit hard to solder. But from the connections between the layers, there was no issue. I saw that there would be an issue because these are very small interconnects, right? But sometimes you can have, if you have more than 2 layers, let's say a 4-layer stack, then sometimes you have vias or connectors, yeah, which go from top layer to the first inner layer, but they don't go through the complete PCB. And the process which I ordered for your designs, they only have through-hole technology. So you can, if you want to connect layer 1 and 2 in a multi-layer PCB, you have to go to drill a hole through all layers. But since we have only 2-layer CP, this question doesn't arise, because if in the moment you connect top layer with bottom layer, you go through the complete PCB. So there is no issue with the connections between the layers. It's only the advice maybe change due to soldering issues to THT, to through-hole technology. Okay, does it end the question? Yeah, thanks. You're welcome. Fine. Okay. Before we continue towards Gerber submission, yeah, any questions from your side to layout or mechanical issues or points? Okay, if it's not the case, now we talk about the Gerber submission. You have done now the schematic. You have a beautiful layout. Maybe after our review class now, you go back and you change your layout a little bit, no problem. But then your schematic should be error-free, ERC-free, and your layout should be DRC-free. And then you say, okay, I print now, or I export now the Gerber files. To do so, please be sure before you export that on the PCB, it has to be unique and really labeled on the silk screen on the front layer. You can also put it on the back layer, a back silk screen, your name, your university, revision, and year. Because when I get the boards back, and sometimes they are, let's say, delivered to some other guys or some other colleagues from me, and then it's good if already on the PCB you can see, oh, this is Valencia, so you know, Mr. Banwa Stefan was in Valencia, so maybe these PCBs are for him. And also for you, when I ship them to you, that everybody can get his own PCB. Good, so this is like organizational stuff. Now, what you have to submit is all the production data has to be zipped in a zip file named NE555, your name.zip. And inside the zip file, the following has to be contained: the HCAD layer, the front silk screen, the front mask, the front copper, back copper, back mask, the back silk screen, So this is a part of the Gerber export, and then you have also manually export the drill data of plated through holes, PTH, and the drill data of non-plated through holes, NPTH. And all this is always one file, and these files you zip together to this zip file and you send it to me. No, you upload it. I will put an upload link again, submission in Nextcloud, and then you upload it there until the deadline, and then we collect the data and give it to our manufacturer. So that's how we do it. Yeah. Good. For the final project, submit your final project in your Gerber files. After the meeting, you can make the last change to your PCB. As I said, if you like, you can export your final PCB to the Gerber format and upload your Gerber files until Sunday, 26/06, 24. What did I do? This should be until Sunday, right? So 1 second. It was a typo. Then if we do so, if you submit it, in this case, your PCBs will likely to be manufactured until the 7th of June. So we collect them on Monday and check them a little bit, and then we give it to the manufacturer. Yeah, and put the Gerber files here. Is this reasonable for you until this Sunday, or should we extend the deadline to the next Sunday? So this would be the 2nd of June. You have time to finish your layouts and upload this weekend, or should I give you one more week? It's also fine for me.
I think it should be better to give us one more week because we have a project to hand in this Sunday specifically.
Okay. Okay. So and for this, so I give you one more week, and that's fine then for you, or you have another project next week too, beside my one.
Well, we have exams, but
Okay.
we are having exams the whole month, so I'm not gonna try to having you delay the deadline for too long.
Oh, okay. So we just we shifted 1 week, and that's fine.
Yeah, I think that's fine.
Okay. So wait. So this would be the 1st, the 2nd. Correct. Of course, this cannot be held anymore. Then we say also delayed to the 14th of June or something like this, or a little bit later. But I think it doesn't change a lot. Okay. Well, so I'm at the end of my presentation. I will upload the presentation to the Nextcloud folder. I think you have access to the Nextcloud folder, right? You should have. I mean, there are folders where you can only upload, but for the download folder, you have access, right? Or should I post the link again?
Yeah, I think we have access. At least right now, I can upload files.
Okay, can you download also files? Do you have another link for downloading files?
Can you repeat the question?
Do we have a download link? Because I have also some material which you should be able to download from the Nextcloud. Right?
I don't know if we have any download link. Like from what I can read from the email that our teacher sent us,
Yeah.
it only specifies the link for the cloud.
Okay.
To upload our projects, but I don't see any download link for other resources.
Okay, wait, I try something. Normally, is it normally? Here. So, wait, I will just put a link into the chat. In the chat, and you try. You can immediately try. Yeah. So I give you this link to all. So now try this link, and you should be able to see. You should be able to see stuff to download.
Yeah, now I can see a folder which can be downloaded.
Yeah, exactly.
Yeah, I guess
So,
that's it.
okay, perfect. And submission you should be able to see, and you can when you submit your Gerber files, it's going to 02 Gerber files with the upload link here from with this upload link. And I put here you see the NE555 timer PPT and Valencia KiCad training organization. And I will also put this presentation here so you can have can check again, and you have also the upload link for your Gerber files. Okay, good. So that's from my side. You have any questions, or somebody from you wants to present his design and have specific questions we can discuss together? Then this would be now the moment we can do it. Okay, no questions?
The Gerber file that we upload, is anybody going to check them? They work correctly, or if they don't, that's our problem.
No, nobody's going to check it. It's let's say your problem.
Okay.
Okay, because in reality it's the same. Let's say the interface between you as a designer and the layouter to the manufacturer are the Gerber files. So and this is what we want to train with you here at this point. Yeah. So the manufacturer, also the manufacturer where I give them, they are going to check if these Gerber files are able to be produced. So if the data, which is the data files, can be produced. But he is not checking if it's making sense what you hand in. So if you make holes where you want and you make shortcuts and where you missed up your power lines and ground lines, he doesn't care. He makes no electrical, or let's say some logical checks, or some checks if it's reasonable to design. He only checks, can I produce this board or not? That's the only question he answers you. So you are at this interface, you are responsible that you hand something in which is correct in the sense of electrical engineering.
All right. Okay.
Okay, but yeah. Good. No, I got a question. There's a problem if a component is not exactly the same. That's yours. No, that's no problem. I mean, when you get back the PCBs and you want to assemble, then it should be components similar to our components. But yeah, if you have this component at stock at your place, or you can order it, it's fine. Good. More questions? Good. Fine. If there are no questions, I must thank you again for your attention, for your time. I must say, yes, as I said in the beginning, I was quite happy from the feedback and the amount of PCBs which you sent to me. And yeah, I'm happy that you obviously like this course and the training. So now I can only encourage you to send me your Gamma files that we can produce it. And I think I will try and send them to you since they are coming back in the middle of June. I will ship them to Valencia. Latest, I can bring them to Cluj. I think most of you are coming to Cluj for the project, right? So we will see us there again. And yeah, wish you all the best. Thank you very much. If you have any questions coming up in the next days, in the next years about PCB, manufacturing, layout, don't hesitate to contact me. It's a pleasure for me to give you some advice and help. And also, if maybe later on you want to make a term abroad at our university as exchange students, we can find projects in this direction. We also have some very strong, actually, embedded design, embedded lectures for C and C++ programming on STM microcontrollers. So I can also suggest this. So if you have any questions or ideas like this, just contact me and we will see what we can do and help you. Okay. And as I heard, your things are coming, exams are coming up. I wish you good luck with your exam and success. And then see you latest in Cluj. Bye-bye.
Bye, thank you.
Bye. Thanks.
Thank you, Stefan. Bye. See you.
Bye. See you.